R1 plus P1 plus R2 plus P2 and so forth. A Hamiltonian for two identical particles might look like this. And notice that in both cases, if you interchange R1 and R2, the physical operator doesn't change. Another example that I'm going to use in a moment is the total spin, S1 plus S2 squared. Suppose we have two spin 1/2 particles. And what I want to look at is the different possible states. So I want to start out with the state psi. It's going to be alpha times plus minus plus beta times minus plus, where of course for normalization alpha squared plus beta squared is going to equal 1. And you know, the term for the fact that if you have two electrons, one spin up, one spin down, we have all these different states from arbitrary complex alpha and beta. That's called exchange degeneracy. It's of course a mixed number because the states aren't necessarily degenerate. But anyway, that's what it's called. So I'm going to put this close. Now, we know what the eigenstates are of S, which is S1 plus S2 squared. There's the triplet state, which is 1 over root 2, plus minus plus minus plus, and this is the triplet state with Z component 0. And then there's the singlet state, which is 1 over root 2, plus minus 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 plus. So we can re-express psi in terms of these two states, and if we do, what we get is 1 over root 2, big bracket, alpha times, well, let me first of all just do the arithmetic explicitly so that we don't lose track of what's going on. The state 1, 0 is that, and consequently, if you add the states together, 1, 0 plus 0, 0, what you get is this one cancels, but you get two of these. So you get root 2 times this, and so if you want plus minus, then you have to divide by square root of 2, like that. Similarly, minus plus is equal to 1 over square root of 2, 1, 0, minus 0, 0. So those are the two states there. And now we can re-express this state psi as alpha times plus minus. So let me have 1 over root 2 out in front. And it'll be alpha times plus minus. That will be alpha times 1, 0 plus 0, 0 plus beta times 1, 0 minus 0, 0. Okay, so that's our state psi. Now we can consider what the mean value of the Hamiltonian is in this thing. And so we call psi H, psi using this one for H, not this one, which is more complicated. You're going to get two factors of root 2, and so we're going to have a 1/2. And then this is going to be alpha star 1, 0 plus 0, 0 plus beta star times 1, 0 minus 0, 0. And then you have H, which is a G S1 plus S2 squared. And so I'm going to pull the G out here, and then I'm just going to call it S squared. And now it's alpha times 1, 0 plus 0, 0 plus beta times 1, 0 minus 0, 0. Okay, so that's the expression. Now you see that, of course, where shall I write this? Maybe I'll write it over here. S squared on 1, 0 is H bar squared times 1 plus 1, 1, 0. So that's 2H bar squared, 1, 0. On the other hand, S squared on 0, 0, which is 0, because the spin is 0. It would be H bar squared, 0 times 0 plus 1, which is 0. So what happens over here is we get G over 2 alpha star 1, 0 plus 0, 0 plus beta star 1, 0 minus 0, 0. And then this acts in here to give us 2H bar squared alpha 1, 0 plus 2H bar squared beta 1, 0. And now the 1, 0 states are orthogonal to the 0, 0 states. If we pull out the factors of the 2H bar squared and the G over 2, we get GH bar squared. And the bottom one, the top one then is alpha star 1, 0 plus beta star 1, 0 because and the bottom one is alpha plus beta 1, 0. This is because we can forget about the 0, 0 states because they're orthogonal to the 1, 0 states. And then recombining this gives us GH bar squared alpha plus beta squared times 1, 0, 1, 0. Because this can be rewritten as alpha star plus beta star times 1, 0, and this is alpha plus beta 1, 0. So the final answer is just GH bar squared alpha plus beta squared. So you see, the energy depends upon the values you pick for the complex numbers alpha and beta in this spectrum of states that are called exchange degenerate. And of course we know which state is the physical state. The physical state is the one that satisfies our criterion here that the states that you should have a symmetric combination if the spin is 1/2, 3/2, etc. in general, 2n plus 1 over 2 h bar. I'm sorry, minus. And these things are called fermions. And then on the other hand, if they're bosons, then it should be plus minus, plus for the spin n h bar, where in both cases n is an integer. So in this particular example, then the physical state
psi physical is then 1 over root 2 plus minus 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 plus. In other words, beta is equal to minus alpha is equal to 1 over minus 1 over root 2. And you notice for that case, the value of the energy, the mean value of the energy, in fact, the value of the energy is 0. In fact, it's an eigenstate of the Hamiltonian now, because this is the state of, this is the state 0, 0. And so H on 0, 0, which is H on psi physical, is 0. So I thought this was a somewhat better example than the one where you had to measure the x component of both spins, which everyone did last time. So are there any questions about this? Relevant to this? Or irrelevant? The strange thing about this issue of identical particles is that the rule that comes out, this rule here, is so simple that when I teach Physics 102, I explain this rule in detail. I don't try to justify it, but I certainly explain the rule. And of course, it has many, many implications. So let me again point out that you can actually start with the state psi 0 equal to plus minus, and then you can act on psi 0 with a physical operator, e to the minus the total spin dot x hat, rotation by pi, and then divide by h bar, and act on that on the state plus minus. And this then will be e to the minus I, the h bars will cancel, we'll have sigma 1 plus sigma 2. Now though, pi over 2, and it will be the x component in each case. So sigma 1x, sigma 2x on plus minus. And as you know, e to the minus I sigma x pi over 2 is cosine pi over 2 plus I sine, well, minus pi over 2. So sigma x. And so this is just minus I sigma x. And so what this does is this gives you minus I sigma x on plus, say, sigma x 1, and minus I sigma x 2 on minus. And as you know, sigma x looks like this. So sigma x plus is minus, and sigma x minus plus. And so this just gives you minus twice minus I squared times minus plus. And so, in other words, the physical state is just the state to start with, plus a physical rotation dot x hat over h bar on plus minus, and this gives you then plus minus 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 plus, which is a physical combination. Then of course you have to normalize it. So let's As I said, in all the examples I've looked at, this rule actually worked. Okay, so now we want to see some various applications. And let's see. One, let's see. Let me go back to the case of atoms that we were talking about when we did perturbation theory. The Hamiltonian for the atom is going to be the sum, say, J equals 1 to Z of J squared over 2ME. One thing I probably forgot to mention over here, when I said that this Hamiltonian was symmetric under the interchange of labels, of course there's no need to put a 1 here and a 2 there because the particles are identical, so they have the same mass. Similarly over here, because all the electrons are identical, it's the same mass here. And then there's going to be minus, if we want, we can say MKS units Q squared over 4 pi epsilon 0, sum J equals 1 to Z. Then we have the Z here, and 1 over Rj. So that's the interaction of each of the electrons with the nucleus. And then the next term, the term that's really quite hard, is a sum over J, let us say J less than K, and then it would again be Q squared. This would be a plus sign over 4 pi epsilon 0, 1 over Rj minus Rk. Okay, so this would be the full Hamiltonian, and we go up again to Z. And you can see that this would be a terrible, difficult problem to solve in quantum mechanics, in fact, even classical mechanics, certainly quantum mechanics. And so what one does is this central field approximation, which I think is quite cute. So you see what you could do, one possibility, or the first thing that would occur when solving it would be to say that H0 is just the sum of Pj squared over 2ME, all equal to E, minus ZQ squared 1 over Rj. You might say that this is H0, and then you might say V then is this this thing, and of course this thing is actually, you remember the identity that in the units, the one thing that saves us from going completely mad with these different systems of units, that this is E squared, where the E squared is the E squared of the E squared, so it's the E squared over H bar C is 1 over 137. So, anyway, so we might write this then as simply E squared sum J less than K 1 over Rj minus Rk. So you might think, well, that's the right way to separate things out, but this is really a mistake because this perturbation is much bigger than it need be, and I mean, the advantage of doing it this way, though, is that you can solve all of these guys. These guys would all put the electrons in really close to the nucleus, and then this perturbation would spread them out again. And it would be it would be easy to do, but it would be a very bad approximation because you know the electrons aren't all clustered near the nucleus. They're spread out because one electron screens another. because of this repulsive interaction. So what you do, and this is, I'm not an expert in this. This is something that I think is more art, is more art than science. You keep the kinetic particle, and then you put in minus V central at Rj. So this is what sum. And let me just write this. Okay. And this V central of Rj is really a symmetric potential. That is to say, V central of Rj is V central of the length of Rj. And then you have as your perturbation V. You first of all put back this thing, and so I'll write this as minus E squared sum 1 over Rj, j equals 1 to z. So I'm putting this back in. Then I'm taking out this one. So I put it in. And this is just the length of that. I shouldn't really have done this. I should have made this just the length of Rj. EC of Rj. So you put in these terms. So that puts back in this one and actually, if I've done it, okay, this I'm screwing this up just a little bit. Okay. This is minus. Sorry, I'm doing this without the notes here. So this is the attract. You put back in the attractive term, and you cancel the thing that you put in. And now you put in the hard term. Okay, so now this is your perturbation. And what you do here is you put in your best guess as to what the physical screened sort of a mean field approximation is. And if you think about it, you'd see that the physical potential is going to look like, it's going to look like minus ZE squared over R for small r. On the other hand, let's suppose that one then goes like this. On the other hand, it's going to look like this one, which is minus E squared over R for big R. And in between, it's going to interpolate between the two. So your V central then is going to do something like, well, let's see, this is not right. Yeah, V central is going to essentially do this, and the one that I, so this is, well, here, let me do this. This one is minus E squared over R, and this one here is going to be V central. Okay. So, and how you do that is a matter of both art and science. But when you do that, then you get as your ground state the eigenfunctions of this Hamiltonian, which put the electrons in suitable shells, and then you use this as your perturbation. And of course, since they're electrons, then the thing has to be totally anti-symmetric. And one way of making things totally antisymmetric is to use something called the Slater determinant. And so the idea that inside of xn is the suitable normalization factor, called C, and you have determinant, and you have say phi 1 of x1, phi 2 of x1, phi n of x1, and then down here you have phi 1 of phi 2s of x1, phi 2 of x. Got this back. Well, when doing that one, that was this x2. So this should be x2. And this is phi 1, phi 2, phi n of x2, and then down here phi 1 of xn, phi 2 of xn, phi n of xn. Okay, so that's a Slater determinant, and these things would involve spin as well as space indices. Okay, so let me see this. Okay, so I get a picture. Okay, here's a picture of how these things work out. Of course, way down in the bottom, we're going to have 1s, and it will have 2 electrons in it. And then higher up, we'll have a 2s level, which can have 2 electrons in it. And then somewhat higher, a 2p level with 6. And of course, the 2p is higher than the 2s because it gets away from the origin more than the 2s. And so down here in this 1s level, we're talking hydrogen and helium. Up here for the 2s level, we're talking lithium and beryllium. Up in the 2p level, we've got boron, carbon, nitrogen, oxygen, fluorine, and neon. What is meant here is that the highest energy electrons are in the 2p level in these atoms. And then we have a 3s level with 2 states, and so this is sodium and magnesium. And then 3p, again 6, and we've got aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And then things get quite tricky. We've got a 4s with 2, and then curiously a 3d with 10, and then a 4p with 6. And this group is, this one is potassium and calcium. And then the 3D, so the 3D group is, I guess, scandium, God, I don't even know what these names are, Ti, there's chromium, manganese, iron, cobalt, nickel, copper, and zinc. Well, I think I'll quit here because I'm not tall enough to continue. But you see what basically the picture gets more complicated. Did you have?
I have a notational question. I'm trying to find the Z that's up there matching the Z over here, and I don't find the Z in the following.
There's a Z here. Is that what you meant?
No. It's a coefficient of Z at the top of your Hamiltonian at the top. There's a Z in front
Oh,
of
there should be a
square.
Z here.
Okay.
Is that it? Thank you. That's good. Thank you for pointing that out. Okay. Now, of course, these identical particles are, as I said, it's very important to have. Well, let me just mention a few, some of the low-hanging fruit here for identical particles. First of all, I just want us to say something qualitative about these different states. For fermions, let's say two fermions would spin up. Then the momentum states or position state would have to be this K prime, K double prime minus K double prime, K prime. On the other hand, bosons, say they're spin zero bosons, then you can have three states. You can have K prime, you can have K double prime, and you can have 1 over root 2 K prime, K double prime plus K double prime, K prime. So these are three states. For Maxwell-Boltzmann, you can have four states. You can have K prime, K double prime, K double prime, K prime, K double prime, and K double prime, K prime. Okay. Now, so for fermions, having K equal to K prime equal to K double prime is impossible. You have to have them not equal. For bosons, you could have K prime equal to K double prime, certainly, and also for Maxwell-Boltzmann. And now, how about the number of states that have, if we assign equal probability to each of these possible states, what's the situation? Well, you have zero states, zero fermion states where they're in the same state. For bosons, you have two states where they're in the same state. And for Maxwell-Boltzmann, let me see, if I have this somehow again. Right. So here is 2/3 of the, if K prime and K double prime are different, then here in 2 out of the 3 states, the 2 particles are in the same state. Down here, it's in 2 out of 4 states, and here it's 0 out of 0. Well, that doesn't, obviously that doesn't compute, that doesn't mean it's 1. So in other words, bosons cluster more than Maxwell-Boltzmann particles. Bosons want to be in the same state more than Maxwell-Boltzmann particles.
And really 0 over 1. 0.
Thank you. Excellent reference. All right, so that's just one little topic there. Let me see what else I was going to say. All right, well, suppose. So anyway, so identical particles then is an important concept and it has huge physical implications. It governs the structure of atoms. It determines the shell structure of atoms, as we've seen here. It also determines the shell structure of nuclei. And back in the 70s, it was one of the reasons why people suspected that there was another quantum number involved in quarks, namely that there was a particle called delta plus plus, and it seemed to be then 3 up quarks. And since it was the ground state of this resonance, they were all thought to be in S states. And these each would have charge two-thirds of the charge of the proton, say. And so altogether, then 3 times 2/3 is +2. That's why it's delta plus plus. They're in an S state. And moreover, the spin was 3/2. So if they're in an S state, then they all had to be spin up. So it had to be U quark, spin up, S state, U quark, spin up, S state, U quark, spin up, S state. And that looked like a violation of spin and statistics. And so what people said was, aha, there's a third quantum number, color. And so, in fact, this guy is red, this guy is blue, and this guy is green. And then one has the possibility of having it totally, you make it totally anti-symmetric. Okay. Identical particles, this concept of identical particles occurs all over. And as I said, low temperature, the things of bosons, you have Einstein condensation, all the particles want to go into the ground state. If you have fermions, on the other hand, you can only put one particle in each state because and it's often true that the Hamiltonian doesn't involve spin. If it doesn't involve spin, then you have 2 possible spin states. And so if you have n particles and you have a fermion, then you put your total energy is E1 for the lowest state plus E2 plus E3 plus ... plus En. And this highest energy then is called the Fermi energy. And if you want to put another particle in, it's got to go in to En plus 1. And so, as I said, if spin is not an issue, then E1 might equal E2, and E3 might equal E4, and so forth. On the other hand, for bosons, and this is the ground state, I should mention that. This is the ground state of the system for fermions. For bosons, on the other hand, ground state is E1, E equals N E1, everybody in the ground state. So, of course, there are many, many other applications. We could probably spend the rest of the semester on identical particles, but I think we want to just see a few more examples and then go on to other things. There are cases, though, when the identical part, when you don't need to take into account the fact that the particles are identical. And this is when, for example, you're doing an experiment here in region A, and then you're doing another experiment here, but somebody else is doing an experiment in region B. And so you have here psi of x is 90 to 0 for x in region A, and then chi of y, maybe I should say chi of x. Pi of x is not equal to 0 only if x is in region B. And in this case, then, let me call this phi instead of, I'll call it phi and chi. So then psi of x1 and x2, you might start out by writing with some normalization factor, phi of x, phi of x1, phi of x2, plus or minus phi of x2, chi of x1. So you might start writing it, say, that way. But then, if in fact x1 is always, if x1 is always in region A, and if x2 is always in region B, for the simple reason that x1, say, is an experiment at, in SLAC, and x2 is an experiment at Argon or Fermilab, then you don't expect them to interfere. And in that case, in fact, the first term would be non-zero, but the second term would be strictly 0, because phi, when x2 is in, say, Illinois, the phi is 0, and when x1 is in California, chi is 0. And so the interference term goes away when the particles don't overlap, because they're in different experiments. Plus, that's pretty important, although if it weren't the case, we simply go crazy. We'd have to know about all the electrons in a different galaxy before getting anything right on any experiments at all. All right. Now let me before going to helium, which is what I want to do next, the helium atom. Let's do something called the variational method. Let's describe the variational method. This is a very simple, very versatile, and at times very powerful idea, although it doesn't always work. In fact, Feynman once wrote a paper on how badly the variational method can fail for quantum field theory. Okay, so first of all, it's clear that what's the variational principle good for? The variational principle, the variational method, is good for finding, is a way to find the ground state of a system. And it's pretty clear that just from its from its nature, the ground state is the state of lowest energy, so that is pretty obvious. Suppose now psi of alpha, or let me just call it psi. Suppose psi is some approximation to the ground state. Then if psi is some approximation to the ground state, this is some approximation to the energy, and it's certainly going to be greater than or equal to the ground state, the true ground state energy, just because the ground state is the state of lowest energy. What's cool, though, is that there's as you might expect that the variation of h will be 0 when you're at the minimum. That's the way we find the minimum in ordinary calculus, is we differentiate and set the derivative equal to 0. So to find the ground state, that's what we want to do. The interesting thing is that if we have some state psi such that any variation of psi gives 0 for the change in the mean value of h, then psi actually is an eigenstate. And so to see that, let's just write this equation slightly differently. Let's write it as psi. I can't resist pi. Let me call this h bar. Is equal to psi h psi. All right. Now, what's the change in this? Well, the change in both sides will be, first of all, variation in h bar times psi plus variation in psi plus psi variation of psi is then going to be equal to variation of psi h psi plus psi h variation of psi. So that's our equation for this variation. And so now we'll say psi variation of h bar will equal, and now I want to move these things to the
You're missing an h bar coefficient with the second and third term.
Thank you. I was looking for it. There. I really wanted it.
No.
Normally one gets chalk only for answering questions, but sometimes...
Okay.
Oh, and I forgot to give you guys the catch. Okay, so now what does this equation look like? It looks a lot better now. Now what we've got is variation psi h minus h bar psi plus psi h minus h bar variation psi. Okay. And so if the variation of h bar is equal to 0 for all changes in psi, then what do we get? We have 0 is equal to variation psi h minus h bar psi plus psi h minus h bar variation of psi. And now we can say even for variation of psi equal epsilon psi itself. And in that case we get 0 is equal to psi H minus H bar psi. And that means that psi H psi is equal to H bar. And so psi has a mean value that's equal to the lowest possible value, namely P0. And so if the ground state is not degenerate, psi is the ground state. If the ground state is degenerate, then psi is one of the states in the ground state, one of the possible degenerate vectors in the ground state, linear combination. So that is the essence of the variational method. It's not all that, it's in fact extremely simple. So what you do though is, as I said, in the case of the central potential, it's almost as much art as science. That is to say, if you have a given problem, you have to, and you want to use the variational method, you have to think very hard as to what the ground state probably looks like. And then you write your ground state wave function. Suppose it's a function of x in terms of a number of parameters, alpha, beta, and so forth. Let me take 2 parameters, say. And so you might say it's a normalization factor, which of course is defined in the usual way. And then you might say, well, this thing is going to be e to the minus alpha times the absolute value of x, because the thing is spherically symmetric. And then you might say, well, that because the thing is attractive but repulsive at the origin, maybe it has an x to the beta at the origin. So I'm just completely guessing. I'm just giving this as a pure example. But in other words, you choose a certain form, and then you would compute what you would compute h bar, which would be then the mean value here in this state as a function of psi. Maybe I should just say it's a function of alpha and beta. H alpha beta, we'll call this the state x alpha beta, and then you divide by the norm alpha beta, or if it's normalized, you don't have to divide by the norm. And so you compute this thing, and this will give you a function of alpha and beta. Then what you do is you say 0 equals partial h bar partial alpha, 0 equals partial h bar partial beta. And so you then solve for alpha and beta, and then once you have alpha and beta, you compute h bar, and that's your guess as to what the energy is, and your function psi x of alpha and beta is then your guess as to the wave function. And sometimes this works very well, sometimes it doesn't. In fact, one example where it does work pretty well, why don't I use that blackboard over there just to, I think I can do this example without using notes. So let's suppose we wanted to estimate the ground state energy of hydrogen, and here so this is a combination of variational principle with the uncertainty principle. So what would you expect h bar to be? Well, it's going to be p squared over 2m minus E squared over R. And you're going to want to have R and P. So this is sort of this is not quite the variational method, but it's worth seeing anyway. You want R and P, and you want actually, you want R and P to be as small as possible. On the other hand, RP has to be of the order of H bar. And so you get H bar is, let us say, P squared over 2M, and P over H bar then is 1 over R. And so this is minus E squared over R is minus E squared P over H bar. And now we differentiate with respect to P. And what we get here is P over M minus E over H bar. Check the math, okay? So that gives us P is equal to ME over H bar. And now this energy then is ME over H bar squared over 2M minus E squared 1 over R, and 1 over R is P over H bar, and P over H bar is ME over H bar squared.
Down at the bottom, you need P over M minus E squared over H bar, right?
Where?
The last equation.
Oh, E squared. Good. E squared. Good. I would have been looking for that. All right, so what is this? This thing is M over 2 e to the 4th over h bar squared minus m e to the 4th over h bar squared. So altogether this is minus m over 2 e to the 4th over h bar squared. And if we change things a little bit, throw in c squared, we get minus mc squared, minus a half mc squared times e to the 4th over h bar squared, c squared. This quantity here is alpha squared, namely 1 over 137 squared. And this turns out to be the exactly correct answer, minus a half mc squared alpha squared for the ground state of hydrogen. So this was sort of a combination of the absurdity principle and the variational method, but it has something of the two. Now, of course, the fact that we got exactly the right answer was using the uncertainty principle and the variation principle is luck. Normally, what you expect to get is if you use the straight variational principle and one parameter, and you don't work very hard, you expect to do better than an order of magnitude. And if you work pretty hard at it, you might get 20% accuracy, 10 or 20% accuracy. And if you put in more parameters, then you start getting better and better accuracy. All right, let's switch now to helium. And of course, one way to do helium is to invent a central potential that's appropriate, but that really doesn't work so well with helium because there are only 2 electrons, and so the procedure I'm going to follow is one that's works pretty well, but doesn't involve a central potential. And in fact, this calculation, we're not going to finish it today, but we will finish it on Wednesday. This calculation played an historical role in the adoption of quantum mechanics. Because you see, when Heisenberg and Schrödinger produced their matrix and wave mechanics and got really nice, essentially two-order alpha squared exact answers for the hydrogen atom energy levels, all the energy levels. Well, that was great, but on the other hand, Bohr had already gotten essentially the same numbers with his sort of magical mystery tour rules. And so people weren't sure whether quantum mechanics was actually right. I don't think it was in the state of string theory. The string theory is now, but couldn't resist. But it wasn't nailed down. On the other hand, by 1927, some people had done some very nice calculations of the helium atom and had gotten the ground state energy to a few percent. And what they used in particular was the variational method. So this will be an application of both the identical particles idea and the variational principle idea, as well as the perturbation theory and everything else. Maybe I'm going to take these classes off. So what's the Hamiltonian? Well, clearly it can be P1 squared over 2m E plus P2 squared over 2m. So these are the two electrons. Minus 2e squared over R1 minus 2e squared over R2. 2 because we're talking helium. And then the kiloterm, E squared over R12, where it was R12 is R1 minus R2. Sorry. So that's the Hamiltonian. And if we have a Hamiltonian where, say, well, let me just give you the expression here. If we take this to be the perturbation, which is the thing I said not to do in the case of a multi-electron atom, but you can more or less get away with it in the case of helium, well, you can solve this part because this will just be, this is just two hydrogen atom terms with Z changed. And so you can take this to be x1 psi NLM of x2 plus or minus psi 100 x2 psi NLM x1. And notice what we're doing here. This is the space wave function. First of all, let me observe, in this Hamiltonian here, there's no spin. But even though there's no spin, there's going to be a huge effective spin because the particles are identical. And so, the particles being identical, the thing has to be totally anti-symmetric. And so, if we're in the triplet state, then the space wave function has to be anti-symmetric. So this is the case where the spin wave function is, I should say, 1m. And this one is the case where the spin wave function is 0, 0. So if the spin wave function is anti-symmetric, then the space wave function has to be symmetric, and this gives you the thing symmetric. And so the thing is anti-symmetric. If, on the other hand, the spin wave function is symmetric, then we need the space wave function to be anti-symmetric. So according to whether the spin is singlet or triplet, the space wave function is either symmetric or anti-symmetric. And the sentence was too long for me to associate which one? All right.
Now, what is this? We really ought to stop in a second, but let me just write down. Suppose we're in the, suppose we're trying to find the ground state of helium. Well, then what we would have, and this would be pi, if they're both going to be in the ground state, then we can't have the minus sign, so we have to have the singlet state. So we have 0, 0. In this case, this thing is z cubed over pi a0 cubed e to the minus z r1 plus r2 over a0 times 0, 0. So that's our approximation for the ground state. And it's space symmetric and spin antisymmetric. Z is equal to 2, but of course what we can do later on is have Z be a variational parameter. Okay, now what do you get as the energy? Well, the energy here then is 2 times 4 times minus e squared over 2a0. The 2 comes because we have 2 electrons. 4 is equal to z squared, z being 2. And this gives you a reasonable answer. It's 8 times 13.6. It's too negative by about 30%. So this is off by 30%. But of course, this isn't even doing perturbation theory. This is leaving out this last term completely. If you put in the last term, which we'll do on Wednesday, you get a better answer. And let me see. You get an answer that's not bad at all. It's off by about 6% as opposed to 30%. And then you apply the variational method and you zoom in on something that's, let me see, it's off by about 2%. And so when that calculation was done in 1927, and when people saw that they could get ground state of helium to within 2% with very solid calculation and a rather simple calculation, they said, well, this quantum mechanics is for real. It's not just a bunch of magical rules. All right, so Wednesday we'll finish up helium and do, I guess, something else.